Alrighty. So actually, what we're going to kind of do today is art class and shop, but this is the math circles, and so I want to make sure that we get some math in. So I'm going to start with a question, and this time I'm typing stuff instead of writing because my handwriting is kind of nasty. But what are some of the first math questions you would ask little children?
About shapes.
And okay, awesome. And we'll put here about shapes. What about shapes? Anything in particular? I got a question I see on the chat. That's what I introduced myself. Yes, I'll pause. My name is Dave Auckly. I am one of the directors of the Navajo Nation Math Circle project. I try to get out to the Dene community a couple times per year. I grew up in Arizona. My dad is from Switzerland. My dad's family is from Switzerland. My mom's family is from Germany. So just Billigana times four. I work at Kansas State University as a math professor. Hope that. So we have numbers, shapes, somebody says in the chat. So it's really hard for me to see what happens on the chat and scroll that and work the other controls. So if you want to communicate why I'm presenting, please unmute and speak. If your sound is not working so well, if there's somebody else who wants to nominate themselves and say, hey, there was a question on the chat about that, if you pointed out, that would help me. So I see numbers. I'm trying to get.
I always ask about counting. How high can you count?
Yeah.
I would split a cookie in half to give the child half and me half. Except then I would think, no, I'm a bigger person, so I deserve more of the cookie. So I would take 80% of the cookie and give them 10%. And I would say, is that fair? I'm a bigger person. I need more food.
I talk about real life events, like financially, and when they get adults.
Sure. So some things, I think on the one hand, an impression that everybody has about math is that it's about numbers. It is much more than just about numbers. It's about logical reasoning. It's about things that you can figure out. So some of the first things are just, are these the things? Just categorizing things. Of course, how many, you can start just counting things immediately. And so, in fact, this is a great way to turn something that might not look like math into math, is just start asking questions. Well, how many of this would it be? How many of that would it be? So in here, maybe let me start with the art. And then after I start with the art, we will ask some questions and categories and try to come up with some questions to make it more than just art. And then you'll see why it will be called shop class later on. So I'm going to move the camera that I'm using, which is actually a... oh, let me see. I bet if I do this right... Oh, I'm trying to adjust. Oh, that's there. I'm adjusting what I see on my screen, or attempting to. Okay. So one of the nice things to build with are inexpensive items. So one of the common things we might do is use toothpicks and marshmallows to make and have students build. Some issues with that are students might be tempted to eat the marshmallows. Another issue is, you get things that kind of look like a big blob or mess when you do that. So some things that I like better than toothpicks and marshmallows that are also rather cheap are just a regular drinking straw. And using regular drinking straws, you have a lot of ability to either use the bend in it when you want to make joints or making slits in it and putting things together. You can cut the bend off. So now you actually have some issues about how are you going to actually build something with one of these things. And so one thought is maybe you're going to tape them together. And so you can see that I did some versions where I worked with tape. And that's kind of, Another thing that you might try is bending a pipe cleaner and running a pipe cleaner through one end and through another. This starts working pretty well, though there will be some issues that could slip off, is one thing. Another thing that's possible is to make things by putting strings through straws. Actually, when I was putting a pipe cleaner here to make a corner, it didn't go all the way through, and the fact that it can strip off becomes a little bit awkward. Later on you build a big model and then it comes apart. A way that I find that fixes that is to run pipe cleaners not just in corners, but all the way through. Like this. I don't know. We can, if you're having trouble seeing what I'm doing, holler. You're probably not seeing both ends of my pipe cleaners, but I've got 3 pipe cleaners here on the table in the document camera. And one thing, well, what shape that we'd make with 3 pipe cleaners and 3 straws?
Excuse me, but we don't see it. Well,
Uh,
I don't.
That's exactly what I was gonna say too. We don't see your document.
I've screwed up the Zoom then.
Yeah,
Let
you
me,
just have your
let
share
me-
screen up.
Yeah, so, is the share, I see why. Let me stop the share for a second, yeah. Now you see them, so let me go back. So yeah, help me out here. I'm the absent-minded professor. I'm gonna screw up. And so if I'm talking about something and you don't see it. So I was, my first demo was I was putting a straw. Do we see that now? And straws bend, and you can do
Yes.
things like put a slits in straws and start sliding the straws together. So you can make cool things just out of straws with nothing else. Another thing that you might want to do is put straws together. And so you might try Scotch tape, which you see I've got Scotch tape on these, but it's kind of peeled off and it's not part of a model. It didn't work so. One thing that has worked well is running string through the straws and tying them together, but you can do a little bit better. One of the things that does a little bit better is taking a pipe. So first of all, for some parts, if I'm not going to use the bend, I might cut the bend off. And then I could take a pipe cleaner and use a pipe cleaner if I want to make a corner. In fact, this leaves the possibility I could stick another pipe cleaner in here, and so that I could have 3 straws coming together if I wanted to go in a different direction. The trouble with this engineering model is that things kind of slip apart. So one of the things that I find works pretty well, but is still not perfect, and we'll talk about why it's not perfect, is I can run a pipe cleaner through each straw and then I can twist the ends of the pipe cleaners together. Just twist. I'm not going to twist these because that's something even better I should do here. So far, so good. I have some things prepared, but so in fact, I'll do more. So what shape might we make? And then let's try to get some math. So what shape is the first starting shape?
Maybe a triangle?
Yeah, I mean, I'm kind of setting you up for that by putting 3 of these together. Now, one of the things that I noticed when I started doing this, this is actually a part of what you see with applied math, is you can theoretically think, hey, this is a good idea. And then you start doing it in the real world, and it doesn't work as well as you might have thought. If I'm just making a triangle, and I just take these things and I twist the ends together here, that's going to hold together pretty well. I can get a pair of clippers like this, and I could clip off the end. I find that clippers work better for pipe cleaners than scissors. Scissors work better for straws. But then if I want to add another piece in and another piece, the more pipe cleaners I have together, the more of a mess I get. So I'm going to now see if I can switch this to my screen share, turning off this camera to bring up some other things. And so we talked about a triangle, and lo and behold, on the screen here, we now have a triangle. Now, one of the things that I might want to do is, instead of having my 3 pipe cleaners where I have 3 joints come together, I might want to have less joints. And so here suddenly we have a math question of how do we minimize, or what is, I'm in caps. What is the smallest number of pipe cleaners needed? That question is going to become more interesting as we get more complicated shapes. Though, if it was just a triangle, what's the smallest number of pipe cleaners I could get away with?
1.
1. Yeah, I could pick one triangle and just bend it in a circle and twist the ends together. The pipe cleaner holds things together very nicely, makes nice corners. Straws make your edges straight. What's another question you might ask about this? Well, it's a shape. Things about shapes you could ask are properties of shapes. So we could count the number of sides, the number of corners. Another thing, which is really going to be the key thing that I'm going to have us address in this session, is what is the symmetry? So do you see any symmetry of this particular shape?
Yes.
So what do you see?
I see 2 acute triangles.
You see 2 acute triangles. You mean you cut it in
Could be
half?
3 also.
It could be 3. So I see a 2 and a 3. And so part of this is, so let me make some comments here that there's different levels of students that we see. In the chat, I'm seeing somebody saying we're identifying, scaling, isosceles, equilateral, measuring angles, etc. That is perfect if you are in middle school class getting students ready for high school geometry, where they definitely need to be able to classify triangles. You're probably not going to start with your first grader with the word scaling. And so in this session, I'm going to try to show things that will work for a range of students at a range of levels. I think, well, I know that if I ask for a first symmetry, one of the first most common things I get is, what's a term you use with symmetry? So Marge put in congruent. In fact, I'm actually going to follow up on that word with congruent. In fact, I'll follow up on it pretty much now. I'm a little bit expecting somebody would describe mirror. That, oh, I see, I need to click there. And now I can move that down. All right, so here I've got a picture of the triangle, and they see a line, people will see a line through it, and they'll say, so that's the symmetry. It's got this mirror where it reflects on the top and the bottom. This was this what you meant when you said you see two triangles? I imagine it might be. Somebody also said a three, which we'll definitely come to. And let's talk about what congruence is here. So as we do this, I want to put some extra information on the triangle. The extra information I want to put on the triangle is just to keep track of the way we move it. And so here I've just added colors, RGB, red, green, and blue, to the vertices of the triangle on the left. And then I put the colors in a different place. And somehow what I want you to imagine when you see the symmetry is the symmetry is you're moving the triangle. And when you move the triangle, what we're doing is we're turning it upside down. And if all of the things line up, if all of the points line up and we preserve the distances, we say that's a congruence or an isometry. Two triangles are congruent if you can move one to the other. I can take this triangle here with the lot. I can take this triangle here, let's say, and I can move it straight down, and it perfectly overlaps with the triangle on the bottom. That's what it means to say that those two triangles are congruent. Well, one of the things I can do here in my graphics program is this up and down arrow, which means a reflect. I could take this piece and I can switch the top and the bottom. In fact, if I just click this button, that moves it. And what you see is it flipped both triangles upside down. I'll flip them again. Somehow, the reason I have the picture on the left and the picture on the right is when I flip this one, it comes to itself. That's exactly what a symmetry is. So if we wanted to put, I don't know if you want me to type in the terms. I will probably type them in for the notes, but not for the video, because I would rather concentrate on the questions and the things that you don't exactly know the answer to and try to solve that. But the terminology will be congruent. You can move one to another, moving it in a way that preserves distance. And symmetry is a motion that moves the shape to itself that preserves the distance. So when we look at this, well, what was one of our most basic ways to get a math question? We could ask how many? Well, how many symmetries does this triangle have? So we see it's got this reflection through this horizontal line. What other symmetries do we see?
I see three.
You see three. And so what are they? Can you describe them?
I can draw a point from each of the angles to the opposite side, giving me three symmetries when I fold the triangle in half through that on that line.
Awesome. And so, in fact, I was doing my best job of psychic reading before we got started here today. And I produced this picture that I could cut and paste. You meant kind of like this, right? And so it's
Yeah.
got these three lines, one going through this corner, one going through this corner, and one going through this corner. So we certainly have three reflections here. So reflection is you're just taking that line and turning it over where that line stays fixed. But are there other types of symmetries? You might see another type of symmetry in the middle of this. So symmetry is a way to move it. And this is one thing, this is a common misconception. And so this is something that you can do early on, is just move puzzle pieces even with kids. Physical objects are going to work a lot better than looking at graphics. And the graphics here is because I can't bring toys into your classroom just today. Any other ideas? Is reflecting the only way to move something?
I can rotate it.
I love it. So I, in fact, prepared for that as well. And so here is the picture of a rotation. I'm going to do something to make more space on my canvas. Oh, hey, that is easily making more space. Sure. And in fact, I want to show the same kind of picture where I put the red dots. So we could take this and we could rotate it to the left, or we could rotate it to the right, 1/3 of a turn. I think I'll show here with the red dots, rotating it probably to the left, so-called counterclockwise. And so the thing that I want to ask and suggest is that when you talk about a rotation, when you talk about symmetry, make sure you talk about rotation and not just reflection. You see how if I rotate this in the counterclockwise direction, the red moves to where the green is, the blue moves to where the red is, and the green moves to where the blue is. That's how I got from the picture on the left to the picture on the right. And I could rotate to the left or I could rotate to the right. So that gives me that's two non-trivial rotations. Why did I talk about non-trivial rotation? Any guess? Part of this is a little bit just looking at the speech to play sort of a logic game. if I say the first thing I'm going to talk about is making things with straws, and then I just keep talking, at some point, what else do you expect me to say? I probably say the second thing. If I talk about a non-trivial rotation, there better be something that would be a trivial rotation. When we talk about symmetries, we can put all of the symmetries together into a collection, and it'll have properties that if you ever do one symmetry and then do another, if you do a first and then a second, you get a possibly new symmetry. You'll always get a symmetry. So if I first rotate this thing and then I reflect it, so here we rotate, and now if I reflect, it comes to a different position, but it's still moving on top of itself. And so doing both of those, and one really sort of funny one that you can overlook that's even harder to see is than a rotation would be the do nothing. I worry that right now what I've just done is I've taken all the joy out of model building. So I'm going to go back and build models, but if we look, I want to point out just some things here to show where we're going to go. Here we had 3 reflections through these 3 lines. Then we had 2 non-trivial rotations going clockwise and counterclockwise. And we had 1 more, which was do nothing. So we ended up with a total of 6 symmetries in an equilateral triangle. So how can you change the symmetries in something is a question that I'd like to ask and answer with straws. And so to show the concept, I will show a first picture and then a second picture that's, I think, more fun, and it'll show us where we're going. So the first picture along these lines is, if I can figure out how to make this thing scroll further, well, maybe I'll scroll it over this way and scroll up, is here I've got a picture of a square in black, and I've added a red line. The square has more symmetries than the line. I can rotate the square 90 degrees, say clockwise, but if I rotate not the red line 90 degrees clockwise, it gets to something different, which means that I can take something that has a symmetry, I can add another shape to it, and I can break the symmetry. This is the talk about breaking the symmetry. Another question that you might ask is, would it be possible to make your triangle, by maybe having more triangles, have the symmetries of a square? And one way to do that would just be to attach a triangle at random to the square, and then move all symmetries of the square, copying the triangle around, and you would get a collection of triangles that would have the same symmetry as the square. It would be a little bit nicer if I could use symmetries that are already part of the square, like there is a reflection across the horizontal line. There's a reflection across the vertical line. If I took the triangle that had a horizontal reflection and put it across this horizontal line and continued that, I could get a collection of triangles that instead of having a smaller symmetry than a triangle, would have bigger symmetry than the triangle. So let me show that, because this, I think, starts getting pretty, and we like pretty. Do you see this shape? What I've got here is a collection of triangles where there's sort of a square built into it. And I was able to put first one triangle, so its axis went across the center axis of the square. And then I could just move the square around, and we got this pretty shape. So let's make some stuff. I'm going to stop the screen share. I can even take some requests, but then I'll show you something. So do you now see the pipe cleaners again?
Yes.
All right. So if I'm going to make a triangle, maybe I'll use less material, and I'm cutting them in half with my scissors, and I will get one pipe cleaner. And instead of running the one pipe cleaner through one and twisting together, I can put 3 straw segments on the pipe cleaner, and then I can bend, and I can twist this together, which if I decide I don't want this, I can take it apart. I could clip off the end. You see how I made that? So what else would you like to make? And so at this point, students might start making a house, a dog, a hogan, which is actually okay. Though you can give them challenges to make things big. And I actually have some suggestions, but maybe instead of me making the suggestions, are there any requests?
Maybe if you snip some of the straw, that same 3 straws on there. In the middle on all 3.
Uh-huh. And then what should I?
Without cutting the pipe cleaner,
Uh-huh.
but
Oh,
the shape will become smaller.
Yes, I like that. And so actually, instead of trying to do that while they're on the pipe cleaner, I worry that I am enough of a klutz. I would cut these things through the pipe cleaner and the straws. But this is easy, right? I mean, here's the request, and I actually kind of like. So it's a little bit. One of the things you can do with math is not see it as this is just a fixed thing where I just add these 2 numbers or just do this and somebody else tells me what to do. Exploring and seeing what patterns you can make is really kind of, that's sort of the essence of it, is that's the essence of research, is you're going to see what it is that you can do and what patterns emerge, and then you'll start asking questions, making guesses, and figuring out why. So we can do exactly the same thing. Now I've taken my 3 sides and I've cut them into each into 2. And now I could make the triangle again. Bend, bend, bend. I could certainly clip off the extra stuff. I'm not going to do that just yet. Well, maybe I will. Yeah, actually, I will. I like this enough. I will. I mean, we've just discovered something really rather cool here, in my opinion, that definitely deserves more thought and more questions about it. Um, Namely, this is more than just a triangle. It's a triangle where we can bend the end. And we could bend the ends going inward and seeing what happens to the shape. And it goes in a one parameter family. We could do them symmetrically all at the same time. We could do it asymmetric. And we get different shapes. And you can ask, how does the symmetry change if you move two of them the same and one different? We can move from one shape to another. If I move like this is a hexagon. It's not a regular hexagon. You see, I didn't twist well enough, but we can practice this a little bit more and twist even more so it stays together. But there's a whole slew of geometric questions I could ask. What happens to the area of this? What happens to the symmetry of this? What happens to the perimeter? How does the perimeter of this shape compare to the perimeter of this triangle? And how does that compare to the perimeter of this? That's, I think, an interesting question. I think that's a very interesting question. So how does the perimeter of this compare to the perimeter of this? Which one is bigger? Does the bigger shape have a bigger perimeter or a smaller perimeter? Do I need to make some voluntold? And
I believe the perimeter is the same.
yeah, because it's just 3 segments if we count each one of those segments. I'm getting suggestions about making an isosceles triangle. Okay, the math teacher in us is going to be excited about the isosceles triangle. Do you think our students are going to get really excited about an isosceles triangle? Do you think that the students are even going to be excited about making things in the plane? Maybe they'll make a wolf or a sheep or a 2-dimensional house, but I have a guess of what would happen. What do you think would happen if you brought these straws and pipe cleaners into your classroom? Would they just make things from plain geometry?
I was thinking of how I would do a prism.
Prism. And so, you mean sort of putting extra things coming up like this, and then another triangle. I like that. In fact, I think one of the things that would happen is students are going to start making things 3-dimensional instead of just 2-dimensional. And that's one of the joys of these models, is that you can make things that are 3-dimensional with them. I think a natural thing to make here, so I'm just estimating, you can make things nicer if you use a ruler. Maybe a tetrahedron, which, okay, that's the mathematician in me speaking. I think the students might make things more complicated. To some level, there'll be some things that they would be able to make just by fiddling. If they come up with something where they want to make it really, really big, like one of those, big domes shaped structures that you might see in some of the larger towns in some of the playgrounds, monkey bars. Then you can't just randomly make, then you have to start thinking about it. And then as you start thinking about it, you're going to start getting into some really engineering and applied math questions. In fact, one of the things I alluded to, but I didn't answer, is what's the smallest number of things it takes to make, say, a tetrahedron? If I wanted a tetrahedron to take this triangle and put three things coming out of it, meeting at the corner. We could ask the same question about a pyramid. This is a little awkward when I'm just trying to hold it like this. Oops. Here, kind of see, I'm actually going to make one here in a second. I'm not going to give her time to think through this question, but actually asking students to think through what's the smallest number of pipe cleaners, or I've done this with animal balloons, needed to make a cube or a tetrahedron. I think a cube works really nicely. Is a really hard, non-trivial question. It's one that they can answer if they think about it. You could run a session where they might take a full class period to figure out both how many you need as ways to build a cube, ways to build a tetrahedron, and what's the most efficient ways of building it. Turns out I can make a tetrahedron with 2 pipe cleaners and no duplicate edges. I can't do it with just 1. And the way that we build it is not so clear. I'm going to fold one thing into a bit of a Z. See how that's like a Z shape? And I can fold these edges up, and the other thing is going to turn into a Z shape as well. And this is going to give us a really efficient way to build tetrahedron, a pyramid with a triangular base. Be another
Your
name
hands
for it.
are outside the view of the camera.
Sorry. Better?
Yes.
And in fact, I will tell you, watching this on Zoom is really unsatisfying. This would be happier in an in-person teacher workshop where I brought in bags of straws and bags of pipe cleaner. In fact, what I would want to do here is we've got a budget and we have our teacher mentoring program. If you want to try this, first experimenting on your own and then doing it with teachers, with students, let me know. I can mail you a bag of straws or have you buy straws and reimburse you. If you do this and pipe cleaners, I think a bag of straws cost me $3, or just going to the local fast food restaurant, my kids do too often, and then bring back straws. Okay, there you have your straws. And pipe cleaners, we can pay for and either ship or reimburse you for straws and pipe cleaners, and you can do this with your students. If you run one of our activities, we can pay you a stipend. We'll pay you $100 if you do this with your students. And we'll talk to you about it and answer any questions you might have. You see how I've got this shape? Counting the symmetries of this really starts becoming much harder. There are many, many more symmetries than you might first expect. Okay, it has a 1/3 rotation that it's got there. It has an interesting rotation of 180 degrees about these 2 points. You see that rotation? That's a kind of funky one to find. We can do things just like I had in the 2-dimensional shape, where we could take something like a cube and insert a triangle into it to make it have a smaller number of symmetries. I could also try and combining some of these together. So that's a little hard to see. Here's something made out of Zoom tools. That's the same thing. It's a cube, and inside the cube, I put a green tetrahedron. I put a green pyramid made out of equilateral triangles. And this sort of breaks the symmetry. A more interesting thing would be I could take this one green triangle and I could rotate the cube in all possible ways and start putting those green triangles together. Or if I wanted to get fancier, and I might have to lift this up, I could start with something like a dodecahedron. You see this shape? It's got pentagonal sides, the sides with 5 things on it, and it's got a perfect tetrahedron built inside of it. And once I have one tetrahedron, I can look, and this has a 5-fold symmetry, so I could rotate it 1/5 of the way around, and I could put another tetrahedron there. If we kept going, we would end up with something that looked like that. This is 5 tetrahedrons linked together where it's got these pentagonal symmetry built up, made out of straws and pipe cleaners. Trying to put this together, really, it almost hurts your brain a little bit to think, wait, does this go over here or under here? There's a lot of symmetries in there. I'm going to show you a different model of the same thing. I will again have to lift the camera up, I'm afraid. Do you see this? This is all out of straws. This has no pipe cleaners whatsoever. This is actually a model another mathematician invented called the straw. And the way this is assembled is I think the camera is probably doing a mirror image on this thing, but he came up and made scaffolding that you could get on paper that you can cut out the solid lines and use a hole punch to punch out the circles. And then you staple or tape the triangular flaps together. There are very nice directions and videos showing how to do this that I will post online. And then you run the straws through the holes, and then you fold the ends of the straws one end into another, and the result is that. So far, so good. So I hope I'm giving you some ideas of a way you could make some math questions and make some interesting mathematical objects out of straws or possibly straws and pipe cleaners. I'll comment a little bit more. Here at Kansas State University, I was inspired because I had seen at Dene College, we had Bruce Bailey in the physics bus come out now maybe almost a decade ago. And he brought a bunch of PVC pipe, like you would use for gardening or plumbing, and made huge geometric models out of it there in the gymnasium for the STEAM Festival. I thought Bruce is now in the Peace Corps in Africa, so he's not available to bring those up this year. Mateus brought big pieces of PVC and made some funky shapes, both for the math camp this past summer and the teacher workshop affiliated with it in Page, and talked about some topology type questions with it. So there's a lot of math questions. There are some PVC pieces that you can just buy in the store like this and put big PVC pipes together. Oh, I forgot one of the triangles. I'll bring a triangle for the break. We decided that we were going to make one of these things, or easier to see here, one of these, but out of 5-foot long sections of PVC pipe. And we actually did this as an event, and we're going to bring it to Janae College for the STEAM Math Festival and play with students with questions related to these straws and things. I'll show you some pictures about doing it with PVC. So some of the first questions are you could put together a cube and have people look and ask questions about the symmetry, how many pieces, how are they going to put together. We make an event out. Oh, I don't know. Am I sharing my, I'm not sharing my screen properly, so you can't see that, I bet. Let me, oh, here we go. I'm going to do a screen share here. And I'm almost close to an end. Oh, you know what? I'm just going to share the whole screen. Oops, and maybe. Sorry, I wanted to show you pictures from the event. So, you know, we shared food and talked, and we got the undergraduates together. You know, this is a student building a first cube, talk about symmetries of a cube. Then they started putting together different colored tetrahedra where we made corners that look like tetrahedra. And suddenly you have all sorts of math when you're trying to make it, instead of out of straws, out of PVC, it becomes a bigger problem. And it actually becomes something that's memorable. I think one of the things that the math circle model does very well, I'm going to stop this share, and maybe I'll point now here as I'm saying sort of some final thoughts, nearly out of time, is if you're just doing the same thing time after time, life can get dull and boring and you kind of lose interest. It's one of the things why recess is so fun for the students, right? They can go out and do something different. Just doing once or twice a year something that's not like the usual math activity, making models with their hands. You want to be careful to put the right amount of math in it, so make it so that it's not just art, so that you're telling them that art is more fun than math. But if you ask questions about how many, what symmetry, what shape, are these the same or are these different, you can put significant amounts of math into an interesting build project that can be done at different scales.